Determinant is just a value which is associated to only square matrices. Whenever any scalar quantity is multiplied to any one of the row or any one of the column, then the value of the determinant can be multiplied by k directly. So whenever you have any one column or any one row as a sum of two elements, then we can split the matrices. Hello everyone, a warm welcome to one and all. This is Shruti ma'am lecturing in Vidhyaashram, the Temple of Excellence, Mysuru. We are in the second session of the chapter, Determinants. So in the previous session, I have given an introduction about the determinants. That is how to find the determinant of a first order or 2x2 or 3x3 matrices. So in this session, we are going to study some properties of determinants. That is how to evaluate or how to find the value of the determinant according to some of the properties which we will learn next. So before going to some of the properties which is very important, now let us recall some of the factors and also learn some simple properties of determinant. So the very first property which is very simple, if each and every element of a row or a column is 0, that is if all the elements in a matrix is 0, then its determinant value is obviously 0. Because see here, if all the elements is 0, then what is the value of the determinant? It must be obviously 0. So this is very simple and sure that you can understand this. If each row or any column, if any of the row or any of the column is also 0. Suppose think that you have a matrix like this 0, 0, 0, 1, 2, 3 and some -1, 2, -1. So this is the matrix which we have written in the form of a determinant. What is the value of this matrix? This matrix is also 0. So if any one column or any one row of the determinant is 0, or if all the elements of that particular matrix is 0, then the value of the determinant is 0. Next question is here, let A be a square matrix of order 3 x 3, then determinant of Ka is equal to, so the options are given, K into determinant A, K square into determinant A, K cube into determinant A. Next is 3K into determinant A. In previous session, we have learned two problems and we have proved it. That is, determinant of 2A can be written as 4 times the determinant A. And similarly, determinant of 3A can be written as 27 times the determinant A. And this we have learned for 2x2 matrix and this we have taken for 3x3 matrix. Now here, suppose if it is a 2x2 matrix, then determinant of Ka can be written as K square times A. So here the value of K is 2 here. So 2 square is 4. So it is 4 times determinant A. So whenever you have 2x2 matrix, then determinant of Ka can be written as K square into determinant A. Similarly, suppose it is a 3x3 matrix, then determinant of Ka can be written as K cube times A. So this is how we will write based on the order of a matrix and the value of the K given here. So according to this property or using this property, we can clearly say the determinant Ka of order 3x3 matrix can be K cube times determinant A. And this can be verified with this example. Here the value of K is 3 and the order of matrix is 3. So 3 cube is 27 times determinant A. So that is why whenever you have a determinant of Ka of order 3x3 matrix, it can be written as K cube times A. Suppose you have 2 into determinant A there or determinant of 2A of 3x3 matrix, then this can be equal to 2 cube times determinant A. That is equal to 8 times of determinant A. The next question here is, which of the following is correct? Determinant is a square matrix. Determinant is a number associated to a matrix. Determinant is a number associated to a square matrix. None of this. Clearly, we know the definition of the determinant. Determinant is just a value which is associated to only square matrices. Hence, option C is correct. That is, determinant is a number associated to square matrix. We can't find determinant for all types of matrices. That is, we can't find determinant values for rectangular matrices. It is only defined for square matrix. Hence, option C is the correct answer. Next, we will move on to some of the important properties of determinant which helps us to evaluate and find the value of the determinant. The very first property is, if all rows and columns are interchanged, then the value of the determinants remain unchanged. Let me take one determinant. Let me say it as delta. So, delta, I have written A1, A2, A3, B1, B2, B3, C1, C2, C3. So now let us interchange this. Let us transpose this matrix. So then I can find delta dash. So that is change rows into columns A1, A2, A3, B1, B2, B3, C1, C2, C3. So however you find the value of the determinant, you expand through any row or through any column, the value of the determinant will never change. Even though when you transpose, the value of the determinant does not change. So therefore, the value of the determinant delta is always equal to its transpose. So it will never change, it will give you the same value. You can expand either through any row or through any column. So therefore, here we can note that if A is a square matrix, then determinant A is equal to determinant of A transpose, where A transpose, it is A dash is called as transpose of A. As we have proved previously, if you change the rows into columns or columns into rows, the order and the value of the determinants does not change. Hence, note that determinant of A is always equal to determinants of its transpose. Next is, if each and every element of a row or column is 0, then the value of the determinant is 0, which we have learnt previously. So, which is the property? If any one of the row is completely 0 or any one of the column is completely 0 or all the elements of a matrix in the determinant is 0, then the value of the determinant is 0. Next is property number 2. If any two rows or columns of a determinant are interchanged, then the sign of the determinant changes. Let me consider delta. So, A1, A2, A3, B1, B2, B3, C1, C2, C3. So, we know that we can perform elementary operation in a square matrix. So, that is why we can also perform the same in terms of determinant. Let me interchange any two rows here. So, let me interchange B1, B2, B3, A1, A2, A3, C1, C2, C3. So, if you interchange any one of the two rows or any one of the two columns here, so then the value will be always equal to minus into delta. It is always equal to minus delta, which we can verify also. Suppose here, if you interchange any two rows, either the first two rows or last two rows, or the first one and the last one. Similarly, you can take or perform the same thing in terms of columns also. So here, when you interchange the row, if the value of the determinant is, for example, 5 for the first one, then it will be minus 5 only when if you interchange the rows and columns. Only the sign changes, the value does not changes. Next one, property 3. If any two rows or columns of a determinant are identical, then the value of the determinant is 0. Suppose if delta is equal to A1, A2, A3, A1, A2, A3, B1, B2, B3. So, if this is the case, you see here the first two rows elements are identical. I can give you an example of 1, 1, 1, X, Y, Z and 1, 1, 1. This is where the value of the determinant, the columns have same elements here. So, that is the first column and the second. That is, the first column and the third column elements are identical. They are one and the same. If in this case, the value of the determinant is always equal to 0. So whenever you find the value of the determinant in this form, you can clearly write the value as 0 because the elements are identical in any two rows or any two columns. Next. Property 4, if each element of a row of a determinant is multiplied by a constant k, then its value gets multiplied by k. Suppose let me take some delta is equal to ka1, ka2, ka3, b1, b2, b3, c1, c2, c3. So if this is the case which is delta, so let me take this as delta 1. Okay, so if delta 1 is equal to Ka1, Ka2, Ka3, that is when you have any common factor in any one particular row, then you can write it as K. You can take the common factor outside, then you can write the, or you can find the value of the determinant B1, B2, B3, C1, C3, C2 here, C3 here, and that is equal to K into delta. So that is, whenever any scalar quantity is multiplied to any one of the row or any one of the column, then the value of the determinant can be multiplied by k directly. Next. So here is some important note. So by this factor or by this property, what we can say is, we can take any number of common factors from any row or any column. Suppose you have a matrix like 3, 6, 9, 2, 4, 8, 1, minus 1, 2. So if this is the common factor, now you need to find out the value of the determinant. So instead of calculating this, so you can clearly see in the first row 3 is the common factor. Take out 3 as a common factor. So then it is 3 1s are 3, 3 2s are 6, 3 3s are 9. And in the second row also there is a common factor, that is 2. So we can take 2 as a common factor. So it becomes 2 1s are 2, 2 2s are 4 and 2 4s are 8. And here we have 1 minus 1 2. So therefore, I can take any number of common factors from any rows or any column here. And now expanding this, we can find directly the value of the determinant. Next is, if some or all elements of a row or column of a determinant are expressed as sum of two terms, then the determinant can be expressed as sum of two determinants. Suppose you have a determinants in this form, x plus a1, y plus a2, z plus a3, and the remaining elements are same b1, b2, b3, c1, c2, c3. If this is the case, any row or all the rows, it may be possible for all the rows or any one of the rows. Similarly, it may be possible for all the columns or any one of the columns. What we can take is here. So instead of calculating it, it makes easier if we separate it. That we can write x, y, z, b1, b2, b3, c1, c2, c3 plus then a1, a2, a3, b1, b2, b3, c1, c2, c3. So this is how we can calculate. If any one of the row elements or sum of any two elements, then we can separate the determinants and find the values. Next is, if to each element of any row or a column of a determinant, equi-multiplies of corresponding elements of other row and it is added, then the value of the determinant remains the same. Suppose if I take an element x plus ka1, y plus ka2, z plus ka3. So then this is b1, b2, b3, c1, c2, c3. How I can write this here? So clearly we can separate these two. So how we can separate? First we can write this as x, y, z, b1, b2, b3, c1, c2, c3. And next we can write this as ka1, ka2, ka3. Next b1, b2, b3, c1, c2, c3. Again, we can take k as a common factor outside. So whenever you take k as a common factor, this determinants remain same plus k outside, and here you have a1, a2, A3, B1, B2, B3, C1, C2, C3. So thus our value of the determinant will not change. We can split into two more determinants and find or take k as a common factor, which makes simplification easier, but the value of the determinant will never change. So as in the case of matrices, we have learned how to find an elementary row operations or a column operation. In case of determinants also, we can apply the elementary row operations or a column operation to find the value of the determinants. And we should also make a note of it. If any one rule is taken to find a row operation or a column operation, it should not affect any other row or column again. So we should clearly make a elementary row operation to apply only for a particular row or a column so that it will not affect any other. Then only it is easier to find the value of the determinant using elementary row and operation, and also by using all these properties which we have learnt. Now here some simple problems are given. So using the properties of determinants, prove the following. So clearly you see here we have x, y, z, a, b, c, x plus a, y plus b, z plus c. So whenever you have any one column or any one row as a sum of two elements, then we can split the matrices. So here the matrix is given. So let us write this in the form of the determinant. So determinants is x, y and z, and here it is a, b, c. Next let us split this x, y, z. We can also write one more determinant, that is x, y, z. Next here we have a, b, c, and again we are left with a, b, c. So using the properties of determinant. Also we know that whenever any two rows or any two columns of the elements in the determinants are identical, then the value is directly 0. So here clearly you can see the first column and the third column elements are identical. So therefore the value is equal to 0 here. Similarly here the second column and the third column elements are one and the same. So therefore the value can be directly equal to 0. Hence what is the value of this determinant? It is 0. Next one, 1, 1, 1, BC, CA, AB, A into B plus C, B into C plus A, C into A plus B. So first let us add this. So let us perform an elementary row or column operation here and then find the value of the determinant. So here what I will do is, see column 3. C3 dash I will take, can be taken as, so here C1 plus C2 plus C3. Let me add all of this. So then the value of the determinant can be written as, so this is 1, 1, 1, BC, CA, AB. So let me take the third column as a sum of column 1, column 2, column 3 elements. Then it becomes 1 plus BC, multiply this AB plus AC. Similarly, it is 1 plus CA plus BC plus BA. Next again, 1 plus AB plus CA plus CB. See the last column elements, they are same. 1 plus BC plus AB plus AC is nothing but CA, BC is nothing but CB, AB is nothing but BA. So they are one and the same. Now let me take this as a common factor. If I take this element as a common factor outside, then I can write 1 plus AB plus BC plus CA. So this I have taken outside. We know that we can remove any common factor from any one of the row or any one of the column or from all the columns here. So if I remove the common factor element from this column here, then I have left with 1, 1, 1, and here I have BC, CA, AB, and if I take common, they left with 1, 1, 1. Clearly you see the first column and the last column are identical. If they are identical, the value is 0. Therefore, if the determinant value is 0, 0 into anything is again 0. So what is the value of this determinant? It is clearly 0. So by learning the properties, instead of expanding the determinants, by using the properties, we can clearly find the value of the determinants. Next is, they have given the matrix, we have to find the value of the determinant is equal to 4a, b, c here. So let us perform an operation. R1 dash is equal to R1 minus R2 minus R3. So that means the first row elements must be subtracted from R2, then it must be subtracted from R1. Then what happens? So the first element here, B plus C minus B minus C, it becomes 0. Next, A minus C plus A, here it is, we have minus C minus A, it becomes again minus C. So this becomes A minus C get cancels, minus C becomes minus 2C. Next, A minus A get cancels, minus B becomes minus 2B. Write the remaining element as it is. We have B, we have C, C plus A, and here we have C, B, A plus B. Now, expand this with the help of the first row elements. How we are going to expand it? This is 0. The first element is 0. 0 into other determinants will completely become 0. This is plus, minus, plus. Remember the position or signs in the particular position in finding the determinant value. So, for the second one, it is minus, minus 2c. So, delete the row and column here. Then, the value of the determinant is here, B, and here it is B, and here it is C, A plus B. Next we have plus, minus 2B. For minus 2B we have B, C, C plus A, C. So it is B, C, C plus A, C. Now apply the value here. So it is 2C. So this becomes AB plus B square minus BC. Next here we have minus 2B outside, and this becomes BC minus C square minus CA. So multiply this becomes 2ABC plus 2CB square minus 2BC square, and here minus 2B square C. Next plus 2BC square plus 2ABC it becomes. Clearly you can see these terms get cancels. So 2ABC plus 2ABC, that is equal to 4ABC. Hence we have found the value of the determinant as 4ABC. Next, so we have the determinant value must be equal to 4A square, B square, C square. So observe the first row here. We have A as a common factor, second row B as a common factor, and third row C as a common factor. Let me take out A from the first row, B from the second row, C from the third row. Then how can I write the determinant without A? That is, we have minus A, B, C. And here it is A minus B, C. And here it is A, B minus C. Next, again you can observe clearly columns. What is the common factor? A is a common factor. If you take A outside, A into A become A square. If you take B from here, it becomes B square. If you take C from here, it becomes C square. And the elements becomes minus 1, 1, 1, 1 minus 1, 1. And here it is 1, 1 minus 1. Now let us perform an elementary row operation here. Let me take R2 as R2 plus R1. This is the new second row, and let me take R3 dash R3 plus R1. What happens here? So we have here A square, B square, C square, and minus 1, 1, 1 in the first row. Look at the second row. So we have to add R2 plus R1. 1 plus minus 1, minus 1 plus 1, 1 plus 1, which becomes 0, 0, 2. Next is R3 plus R1. 1 minus 1 becomes 0, 1 plus 1 becomes 2, minus 1 plus 1 becomes 0. So that becomes 0, 2, 0. Now expand with the help of a column here. Why? Because already two elements are 0. So expand the determinant where the number of zeros is more in any columns or rows, which we have learnt in previous session. So let me expand it with this. So A square, B square, C square. Now here we have minus 1 into 0, 0 is 0, minus 2 2s are 4. And the remaining are 0 plus 0 because the factor itself is 0. So when you find the value of the determinant, it will become completely 0 there. So therefore here minus 1 into minus 4 becomes plus 4. 4 into a square b square c square becomes 4a square b square c square, and hence we have proved. Now next one is 1 1 1 a b c a square b square c square. We have to show that a minus b into b minus c into c minus c. Now let me take r2 dash as r2 minus r1 and r3 dash as r3 minus r1. So let me write the first one as it is. We are not affecting the first row, we are only finding the values of second row and third row. So our second row elements must be written as r2 minus r1. 1 minus 1, 0. b minus a, b minus a. b square minus a square it becomes. Similarly here r3 minus r1 means 1 minus 1, 0. c minus a, c square minus a square. And here you can see, you can take b minus a as a common factor in the second row and c minus a as a common factor in the third row. So therefore, if you take b minus a and c minus a as a common factor, here you have 1 0 0, a square, and here it becomes 1 b plus a, and here it becomes 1 c plus a. Now let us expand it. So we have b minus a, c minus a, and here we have, see, 1 0 0. Let me expand through column 1. So if you expand through column 1, plus minus 1 plus 1, 1 into, we have the determinant 1 b plus a, 1 c plus a, 1 b plus a, 1 c plus a. And the remaining is minus 0 plus 0 because the value of the determinant starts with 0. Hence when it is multiplied, it becomes 0. So now we have here b minus a, c minus a, and here 1 into anything is 0. So this becomes c plus a minus b minus a. So these two get cancels. So take negative here. When you take minus outside, it becomes a minus b. And when you take minus here, then it becomes b minus c. Here it is c minus a. That is equal to RHS. So this is what we have to prove. So just by applying the properties, we can evaluate the value of the determinant simpler. Next is x plus 4 2x 2x, 2x x plus 4 x 2x, 2x 2x x plus 4. We have to show that the value is 5x plus 4 into 4 minus x whole square. Let me take column 1 as column 1 plus column 2 plus column 3. That is, add all the columns together to the first column. Then it becomes x plus 4 plus 2x becomes 5x plus 4. Similarly, here is also 5x plus 4, 5x plus 4. Write the remaining as it is, 2x, x plus 4, 2x. And here 2x, 2x, x plus 4. Now here take 5x plus 4 as a common factor. If you take 5x plus 4 as a common factor, here we are left with 1, 1, 1, 2x, x plus 4, 2x, 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 x plus 4. Whenever you get any one of the row as 1, 1, 1, perform row operation so that the other two elements become 0. So it will be easier to expand. So what I will do here is I will take R2 as R2 minus R1 and R3 as R3 minus R1. So R2 dash as R2 minus R1 and R3 dash as R3 minus R1. So here we have 5x plus 4 as a common factor and the first column becomes 1, 0, 0. Let's see the second column here. So x plus 4 minus 2x becomes, so the first column will be same, that is 2x and 2x. Only we are applying the rule for second row and third row columns. So now it is x plus 4 minus 2x. It becomes 4 minus x. 2x minus 2x 0, 0. So it is 4 minus 6 and 0. Next, 2x minus 2x, 0. X plus 4 minus 2x is 4 minus x again. So we got 0 here and 4 minus 6. So remember one thing, since this is a square matrix and this is the principal diagonal elements. Okay, when you get the elements under the principal diagonals are 0. Whenever all the elements under the principal of the diagonal elements are 0, then the determinant value is just the product of principal diagonal element. I'll give you an example. Suppose you have a determinant like this. A, B, C, 0, minus 1 and 2 something, 0, 0, B. So in this case, see the principal diagonal elements. This is the principal diagonal element. And below that, all the elements are 0. Then what will be the value of the determinant? It is only the product of principal diagonal. Hence, according to this, the value will be equal to minus AB. So this is one of the important thing you should know while solving the problem. So a shortcut method you can say. So whenever all the elements under the principal diagonal elements are 0, no need to expand. The value of the determinant is just the product of the principal diagonal element. So therefore, I can clearly write 5x plus 4. And what is the product of this? 4 minus x into 4 minus x? 4 minus x whole square. So this is what we have to prove. So this is what the RH is required to prove. Next problem. We have a minus b minus c, 2a, 2a, 2b, b minus c minus a, 2b, 2c, 2c, c minus a minus b. That must be equal to a plus b plus c whole cube. So whatever the same properties and operation we have done to the previous one, the same thing we can apply here. Let me add all the columns here. So the properties and operation which we have done for the previous problem can be applied for the same here. So here we can clearly see when we add all the rows, we can perform an operation for row 1 column. So let me take R1 dash as R1 plus R2 plus R3. So therefore here when you add all this, the first row will be A plus B plus C, A plus B plus C, A plus B plus C. And write the remaining element as it is. B minus C minus A, 2C, 2B, C minus A minus B. Clearly, you can see A plus B plus C is a common factor in the first row element. Let me take it outside. A plus B plus C. So, when you take it outside, you are left with 1, 2B, 2C here. And here it is 1, B minus C minus A. And here it is 2C again. And here 1, 2B, C minus A minus B. Now, here we have 1, 1, 1. I already told you when you have any one row completely 1, make sure the other 2 becomes 0. So for that what I will do here, I will take column 2 as column 2 minus column 1, column 3 as column 3 minus column 1. So this becomes A plus B plus C. So column 1 will be same, that is 1, 2B, 2C, 1, 2B, 2C. Now column 2 is column 2 minus column 1. So that is 1 minus 1. So this becomes 0. Next is we have B minus C minus A minus 2B. So which becomes minus into A plus B plus C. Next is 2C minus 2C, 0. Now the third column is again column 3 minus column 1. Column 3 minus column 1. So it is again 1 minus 1 is 0. 2b minus 2b becomes 0. C minus A minus B minus 2C becomes minus of A plus B plus C. So therefore here we have 0, 0 minus of A plus B plus C. So now you can clearly see here. So here also you can see above the principal diagonal elements here, all the elements are 0. So here also you no need to expand this determinant because it is 1 into minus A plus B into minus A plus B plus C, which becomes A plus B plus C into A plus B plus C whole square. Because the other two elements are 0, no need to expand. So hence we can clearly see the value is A plus B plus C whole cube. So next one, Look here, the determinant value must be equal to 2 into x plus y plus z whole cube. The same properties, the row operation or column operation. First see the value of the determinant. Clearly we can see when you add all the columns in the first column, we will get the same factor. What is that factor? 2x plus 2y plus 2z. So similarly here, 2x plus 2y plus 2z. 2x plus 2y plus 2z. And here x, y plus z plus 2x, x, y, z plus x plus 2y. Next take this as a common factor, 2x plus 2y plus 2z. And here we get 1, 1, 1. Here it is x, y plus z plus 2x. And here it is x, y, z plus x plus 2y. Clearly, to make this as 0, R2 minus R1 and R3 minus R1. And here you can take 2 as a common factor. So when you take 2 as a common factor, it is 2 into x plus y plus z. And applying the row operation, R2 dash as R2 minus R1 and R3 dash as R3 minus R1. Clearly, you will get the first column elements as 1, 0, 0. And the second column element as x, 2x minus x becomes x and this becomes x plus y plus z and it is 0. Again y minus y 0, z plus x plus 2y minus y becomes x plus y plus z. So here it becomes x plus y plus z 0. Here y 0, x plus y plus z. Clearly see this is the principal diagonal elements and below that all the elements are 0. Hence the value of determinant is just the product of principal diagonal element. That is 1 into x plus y plus z into x plus y plus z. And outside we already have 2 into x plus y plus z. So therefore when you multiply all this, this is 2 into x plus y plus z whole cube. That is equal to RHS. So this is how we will prove the value of the determinant using some of the properties of determinant and with the help of elementary row or column operations. So this is an important topic for 4-mark question. So they may ask you to expand determinant with the help of the properties of determinant and this is how we can do. So we'll meet you in the next session with the new concept. Until then, keep watching, keep learning, keep exploring. Thank you.